In this lesson, we will describe how a buffer controls pH and define buffer capacity. Remember that the function of buffers is to resist changes in pH. The human body functions in a very narrow range of pH values, and so our blood actually has several buffers in it in order to maintain that pH. Between 7.35 and 7.45 is considered a normal pH. Below or above this is considered acidosis and alkalosis, respectively. Going too far from our 7.35 to 7.45 range will result in death. When we prepare a buffer, we actually need to add both the weak acid and its conjugate base. So we take a solution of weak acid and a solution of the conjugate base formed from the salt compound and mix them together in order to form the buffer. Different conjugate acid-base pairs result in buffers for different pH values. Remember that buffers can also be prepared from weak base and its conjugate acid as well. You must mix both the weak acid and the conjugate base together in order to prepare a buffer solution. The small amount of the conjugate formed by a weak acid dissociation is not sufficient to create the buffer. Let's look at a buffer prepared from HNO2 and NaNO2. This combination can form a buffer with a pH of approximately 3.3. The buffer is formed by mixing a solution of HNO2 and NaNO2. Note that HNO2 is a weak acid which partially dissociates into forming H plus and NO2 minus. NaNO2 is an ionic compound, so it's a strong electrolyte and completely dissociates into Na plus and NO2 minus. The amount of NO2 minus produced from the dissociation of HNO2 is not enough to create the buffer solution, and this is why we have to add the NaNO2. Note that the Na plus will be present in the solution, but it's not actually involved in the buffering process, and so we treat this as a spectator ion. Let's first look at the pH of water, which is a neutral solution and has a pH of 7. If we add a small amount of acid to that water, we see a pretty significant drop in the pH because we see an increase in the H plus concentration. If we add a small amount of base, such as NaOH, we see a pretty significant increase in the pH because we see an OH minus concentration increase, which leads to an H plus concentration decrease. Let's compare adding acid to water with adding acid to a buffer solution. As we add H plus or H3O plus, we see a very small or minimal change in the pH value. Remember that H plus and H3O plus are the same, and it's two ways to write the exact same thing. A buffer is going to behave like any other equilibrium system, so we can apply Le Chatelier's principle to what will happen in a buffer solution. If we add acid in the form of H+, we will see that our reaction shifts to the left. Once it's shifted to the left, then we will see the HNO2 concentration increases and the NO2 minus concentration decreases. While most of the added H+ is neutralized and reacts with NO2 minus to form NaHNO2, not all of it is consumed, so the pH drops a very small amount. But the change is significantly less than adding acid to water. Let's look at what happens when we add base to a buffer. We will add this as OH minus because we're going to add it as a base such as NaOH or KOH. And therefore we will see a shift, but predicting the direction of this is a little bit more challenging because we don't see OH minus in our overall reaction. However, we do know that H plus and OH minus will react to form water. So if we add OH minus, it has the same effect as removing H plus. And from Le Chatelier's principle that we know removing something on the product side will result in a shift towards the right which will lead to a decrease in the amount of HNO2 and an increase in the amount of NO2 minus. We only see small changes in the pH when we add base to a buffer, unlike adding base to water. Remember that the function of buffers is to resist changes in pH. However, there are limits, and this is known as the buffer capacity, which is the maximum amount of acid or base that can be added before the buffer stops working as a buffer. The point in the middle of this region is the pKa value, and this region indicated by the green lines is the buffering region. So we can consider the buffer as absorbing the added H plus or OH minus, and it can add to a certain point. However, at some point we add so much that we get beyond our buffering region, and as a result, we see that it can no longer absorb or take up the amount of added H plus or OH minus, and it will see a drastic change in the pH as if we were adding it to pure water. We can consider a buffer like a sponge. We can add so much water to a sponge until it can't absorb any more. Buffers are the same way. We can add a specific amount of acid or base to a particular buffer, but at some point we cannot add any more and still maintain a constant pH.